Morning. So today we're going to discuss what is chemical oxygen demand, how to determine the chemical oxygen demand. This chemical oxygen demand is usually called as COD. So what do you mean by COD? So there are two terms. In order to estimate the quality of water, we have two things. One is COD and BOD. COD is called as chemical oxygen demand, whereas BOD is called as biological oxygen demand. So biological oxygen demand, it is nothing but the amount of oxygen required in milligrams or to oxidize only the organic waste present in wastewater, 1 liter of wastewater. So almost all industries whichever we have, it remains effluents. This effluents, where they go, it go finally to the water sources. So as per the pollution control board, the effluent should be treated. So only after treating it should be sent into the water sources. So whatever the waste is present, it will be oxidized by, it should be oxidized inside the campus of the industry, and then it should be sent into the water sources. If not, what will happen? The effluents will go into the water bodies. There it will use the oxygen, dissolved oxygen present, that will get converted to carbon dioxide and water. So in order to prevent this, we are supposed to oxidize the entire thing of waste in our industry itself. So how much amount of oxygen is required to oxidize the waste, and the waste changes from industry to industry, right? So oxygen is also, we are supposed to buy oxygen. So due to the cost of oxygen due to this pandemic, every one of us know the cost of oxygen also, right? So oxygen does not come freely, so we can bridge it freely. For not to oxidize, we are supposed to buy it. So in order to oxidize the waste in waste present in the wastewater, we are supposed to supply oxygen. How much oxygen should be supplied? Then we are going to find out by chemical oxygen demand. So the chemical oxygen demand, or COD, is a parameter. It measures the total oxygen required to oxidize both organic and inorganic waste in sewage water. So what we are going to do, we are not going to directly send oxygen. So instead of that, we are going to use a strong oxidizing agent, that is potassium dichromate. So the amount of unreacted K2Cr2O7 will be estimated against FAS using Fahrenheit as an indicator. So COD is usually defined as amount of milligrams of oxygen required to oxidize both oxidizable and non-oxidizable, that is both organic and inorganic waste present in 1 liter of wastewater using a strong oxidizing agent such as potassium dichromate. So it's very important. So why you are using COD? Because COD is very spontaneous and it gives immediate, whereas BOD, it gives only the oxygen required to oxidize only the organic waste, and it takes minimum 5 days. Okay, whereas COD, it gives organic oxygen required to oxidize both organic and inorganic waste, and it is spontaneous. So a known volume of wastewater will be tried against the potassium dichromate taken the burette using silver sulfate and mercuric sulfate. So what is the use of silver sulfate and mercuric sulfate? I'll tell you. So first we're going to, as you know, every titration you have, all volumetric estimations, you have two parts, part 1 and part 2. So part 1 is preparation of FAS, sand solution. So we're going to take W grams of FAS in a 250 ml sand flask. We're going to add 1 test tube of sulfuric acid. We're adding sulfuric acid in order to prevent the air oxidation of ferrous to ferric and dilute the solution up to the mark using ion exchange water. So by knowing the weight of solute and volume of solvent taken, you're going to calculate the normality of FAS. So later, we're going to pipette out 25 ml of the given wastewater sample. We're going to add 25 ml of potassium dichromate. As soon as you add potassium dichromate, what happens? The potassium dichromate oxidizes the both organic and inorganic waste present. So to that, we're going to add 1 test tube of dilute sulfuric acid, which is a mixture of silver sulfate and mercuric sulfate. So silver sulfate is added as a catalyst, which catalyzes the oxidation of straight chain hydrocarbons. So silver will get precipitated as silver chloride if chloride is present. Okay, so if chloride is present, silver will precipitate silver chloride, and also the silver chloride PPT we cannot it will disturb in determining the end point. So in order to maintain silver sulfate as silver sulfate itself, we are going to add mercuric sulfate. So before silver comes and attacks chloride, mercury attacks chloride and forms mercurous chloride, and silver remains as silver sulfate itself. So we're going to put out 25 ml of wastewater into the beaker, the conical flask, that we're going to add 25 ml of dichromate. When you add dichromate oxidizes the entire organic and inorganic waste into carbon dioxide and water. Out of 25 ml, only 10 ml will be oxidized, will be used up, or 15 ml will be used up. Remaining 10 ml will be unreacted. That unreacted potassium dichromate will be estimated against the Fa is taken in the burette using Ferroin indicator. So you get the end point will become bluish green to reddish brown. So now I told you only 15 ml is used, 10 ml is unreacted. How to know 15 ml is used? In order to know that we're going to perform a blank titration, we're going to put out 25 ml of K2Cr2O7 into a clean flask, add one test tube of sulfuric acid and indicator and titrate. So here now blank means we're going to add everything except the sample. So what is sample here? Wastewater. So we're going to exclude. So now we're going to come to know how much volume of FAs is required to neutralize the K2Cr2O7 taken in the conical flask. Right. So similarly, if 30 ml is required, then there how much it is? Unreacted only 10 ml. Right. For 10 ml how much? By knowing the difference between the blank titer value and sample titer value, we can conclude how much volume of K2Cr2O7 is required to oxidize the waste present in wastewater. By knowing that, we can calculate the COD. So COD is given by 8000 into y minus x into z milligrams of oxygen divided by 25. 8000, y is blank titer value, x is sample titer value, z is normality of K2Cr2O7, and 25 is your volume of sample taken. So the small demo here, you can come to know how the experiment is carried out. Okay.
Next experiment is COD of the given wastewater sample, that is chemical oxygen demand. It is the amount of oxygen required for the complete chemical oxidation of organic and inorganic matter present in the wastewater sample by using a strong chemical oxidizing agent like potassium dichromate. For that we are starting the demo. Part A is preparation of a standard solution. The salt here is a FA salt. Ferrosodium salt will be given to you. First we have to wash all the apparatus cleanly with the distilled water. Then weigh the given salt and transfer it to a cleanly washed 250 ml volumetric flask and add one test tube of the given 1:1 sulfuric acid. You have to add first H2SO4, then you should add water. First you should add sulfuric acid to the salt, then you have to add the water. We are adding H2SO4 to prevent the hydrolysis of FAS salt into ferric. FAS into ferric salt. We are adding H2SO4. Then next step, when you prepare the solution up to the mark, you will be getting a solution like this. I have already made this. Okay, after making up to the mark, you have to mix it very well and fill in the burette. Very simple. Weigh the salt, transfer it to your 250 ml volumetric flask, add one test tube of H2SO4, make up the solution accurately up to the mark, mix it well and fill in the burette. Okay, so part A is over. Part B is we have to pipette out 25 ml of the given wastewater sample. The given wastewater sample, and we should also pipette out 25 ml of the oxidizing agent potassium dichromate. After all the solution run out, you have to touch the tip of the pipette 2 to 3 times to the bottom of the conical flask. and then add one test tube of H2SO4 containing silver sulfate and mercuric sulfate. Silver sulfate acts as a catalyst in oxidizing some of the organic compounds, and mercuric sulfate is added to bind the chlorides which is present frequently in wastewater samples. And then we have to add a few drops of ferrine indicator. This is ferrine indicator. Its chemical composition is ferrous 1,10 phenanthrolene sulfate. And important here is you have to add for all the trials same amount of the indicator has to be added. Okay, so you add for each trial 6 drops. 6 drops of indicator you have to add. 1, 2, 3, 4, 5, 6 drops of indicator added. It's important to note that for all the trials, for all the 3 trials, you have to add equal amount of indicator, 6 drops, it's enough. Now you will get an initial color like this. This is called a dirty green color, or this is also called as a bluish green color. Bluish green or dirty green it is called as a. Now we have to titrate against the standard FAS solution taken in the burette until we get a reddish brown color. Almost similar to the indicator color we will be getting. Okay, so water terms we have taken. We have taken 25 ml of wastewater, 25 ml of potassium dichromate, and 1 test tube of the sulfuric acid containing silver sulfate and mercuric sulfate, and 6 drops of indicator. You will get this initial color. Now titrate against the standard FAS solution taken in the burette to get a reddish brown color. When the titration proceeds, the dirty green color will be there. It will be something like bottle green color. It will be turning into. You should keep on adding dropwise.
So you're getting a reddish brown color.
You're almost near to the end point now. You have to add very carefully dropwise. So this is the end point you will get. For the last drop you will add, you will be getting a reddish brown color. This is the final color. And note down the urine reading. I got around 21 ml. 21 ml. In the same way, you have to record final urine reading 21. Trial 2 and 3 also should be done. You have to do 3 trials. 3 trials you have to do. And then coming to the calculation part, the same way you have to record 3 trials. Okay, and you must get concordant readings. And then coming to the calculation part, first you have to calculate the normality of the given FAS salt. First you have weighed the salt taken, right? W1 minus W2 you have to take. That will give you the weight of the FAS Krishna given. You have to multiply by 4 divided by equivalent weight of FAS, that is 392.14. So it will be like this. Weight of the salt given, it may be 4 grams, 5 grams, whatever the salt you got. Weight of the salt to 4 by 392.14. When you multiply, you will be getting the Z normal. You will get Z normal. Then after completing the 3 trials, any one trial you are taking here, any one trial value you have to take. You should not have to take all the 3 average. Okay. Any one value you are considering as a X, volume of FAS consumed for sample titration is equal to X, and volume of FAS for blank titration is YML. This will be given in your exams. You don't have to perform blank titration. Blank titration value will be given to you in your exams. What is blank titration means? It is similar to the back titration, but it does not contain wastewater sample. Anyway, this value will be given to you. Okay. So coming to the calculation part, 8 into y minus x. Y is a blank negative value which is given. X is a purity what we got here. Z is the normality what we calculated there. Into 1000 by 25 will give you dash milligrams of oxygen per dm cube. So finally we will getting dash milligrams of oxygen per dm cube. This is the amount of oxygen required for oxidizing the organic and inorganic impurities which is present in the wastewater sample.
Yeah, this is how we are going to carry. Okay, thank you.